Good morning, everyone. My name is Chawla. I'm postdoc working in UCD with Asifa and Vikram. And today I'll be presenting transverse discontinuity mapping using higher order flight time estimates. So basically, my objective is to just highlight the importance of higher order correction terms while deriving discontinuity mappings of any non-smooth system. So for this presentation, I'll be focusing on two types of non-smooth systems. The first is a hybrid system of the impacting class, basically impact oscillators, where the phase is the variable x is restricted to only one side of the phase space. So the state evolves in the phase subspace Si, undergoes an impact, and gets mapped back to the same subspace using the impact map R of Xi. So basically, the first term in the Taylor expansion of the flow at near the discontinuity boundary is discontinuous. So this is basically a system with degree of smoothness 0. And the second system is a Filipov system where we allow the state variable to cross discontinuity barrier from the region Si to Sj. And at the point of impact, the velocity vector fields Fi and Fj, they are different. So the second term in expansion is different. So such a system is a system with smoothness 1 or Filipov system. So we first consider an impact oscillator. The mass M is undergoing periodic motion externally excited by a harmonic force, and when there is an impact with a barrier located at, for example, x equal to sigma, there is an instantaneous reversal in its velocity defined by a coefficient of restitution R. And this is the limit cycle that we are looking into for this parameter values. Now, the main idea is to understand how orbits behave in the local neighborhood of the primary limit cycle, especially in the local neighborhood of the discontinuity boundary. So in this case, the trajectory comes over here, undergoes an impact at Xi and gets mapped to R of Xi. So the idea is to look at two trajectories. So over here, there are two trajectories. The blue trajectory is the primary limit cycle and the red trajectory is the perturbed path. They are, for example, let's say they are initiated from the same point intersection sigma 1, and the primary trajectory reaches Xi. However, at this instant, the perturbed trajectory has not yet reached the discontinuity boundary, which we are modeling by a scalar function h of x. So there is a time difference that is required for the perturbed trajectory to reach the discontinuity barrier. So basically, we have to calculate this time difference, let's say delta or flight time. So we do that by first looking at the state x0. So the original trajectory reaches Xi and gets mapped to R of Xi via the impact vector over here, R. Whereas the perturbed state reaches x0. The idea is to find out first the time difference, delta, for x0 to reach x2. Then we estimate where x2 is on the discontinuity boundary. And then we try to map the point x2 via the impact map R of x2 to reach x3. And then we basically back traverse it to reach x4 within the same time difference, in a way as if, the perturbed trajectory comes over here to x0, gets mapped to x4. This is the forbidden region because the dynamics shouldn't be in this part of the phase space. But if you wait for a certain amount of time, which is Ti plus delta, there is a time difference, and Ti is when Xi undergoes an impact with sigma, then ideally x4 should reach x3. So that is basically the whole idea, and this is basically the discontinuity mapping that we're talking about. So basically at the point of impact, x gets mapped to R of Xi, the vector, the perturbation gets mapped from y minus to y plus, and state variable x0 gets mapped to x4. So the thing is, this was first derived by Professor Nordmark in 2000 for the impact oscillator case, and by Professor Renkolene in 2002 for the Filipov system. And over here, if you see the time difference, you can see that it results in a fraction which always gives you a finite value for any perturbation magnitude. And the denominator is proportional to x dot. So for very low velocity impacts, the delta tends to blow up. But when we introduce higher order correction terms to the flight time estimate, we get a quadratic equation which tells us that there is a range of perturbation for which impacts might not occur if the discriminant is not real. So this is the higher order of flight time. And so you can basically solve this quadratic equation, and there are two roots, and the one with the positive sign makes sense because in the limit of y tending to 0, the time delta should tend to 0. And for the root with the positive sign gives you that. The other thing is that there are additional terms that comes in the denominator. So if you even just expand, binomial expand the square root term, and you just keep the first term, you get x dot plus the second component of the perturbation. So even for low velocity impact, the delta plus gives you values which are smaller than delta 1. So in a way, the first order correction tends to overestimate the map points x3. So now we have the higher order flight time, which is a quadratic equation, and the mapping of the perturbed path x4 is given by this expression. And so these are basically the higher order transverse discontinuity mapping. Now there is one problem over here. The transverse discontinuity mapping is okay. It's all fine. It works well. But when we're trying to study, let's say, the stability of the limit cycle, we require mononomial matrices and state transition matrices. But when you use the first order theory, what happens is you see that the delta over here is proportional to y minus. So if you plug that in the first, these terms, you can simply take y minus common. And the relation between y plus and y minus can be easily written in the form of a matrix, which is the sortation matrix. But when you're using higher order correction terms, you cannot do that because delta itself is quadratic. So we require a method to somehow get a state transition matrix, which comprises the higher order correction terms as well. So we'll do that later using a numerical method. But these are the results so far. So over here we see we are considering an example where the primary orbit is undergoing an impact. The red trajectory is a perturbed cycle, a perturbed limit cycle, the exact solution, and it does not undergo an impact. And the separation is 0.0095. The first order gives us a real answer, whereas the second order flight time gives us imaginary value telling us that an impact will not occur. And so if you're trying to construct a one-roaming matrix, we don't need to multiply the sortation matrix with it. So, and similarly, these two figures correspond to a condition where impacts are actually occurring. And then there are two perturbations over here. The primary target, the primary orbit is blue. The perturbed trajectory is in red. It gets mapped to the point x4. Now I'm simply integrating the x4 by a time delta forward in time. So what we see is that when we use the first order transverse discontinuity mapping or the sortation matrix, the state x3 is always getting overestimated, and that's because delta doesn't have those additional terms in the denominator. But the second order mapping actually after integration exactly lands on the discontinuity property. So in a way, this is more accurate. So this is just the percentage error of the flight time estimated in comparison to the first order and the second order when we compare the time difference using the actual solution of the perturbed trajectory. Once again, we see that the second order gives us better answers, and in this region, when no impacts occur, the delta plus or delta 2 gives us imaginary values. And you can find out this critical value for which impacts won't occur by simply solving for what value the discriminant is not real. So now we come to a Filipov system where, again, there is a mass M undergoing soft impact with this system. You can find this system in one of the papers by Professor Yu Ma, Professor Mari, and show me through. So we've taken that model. This is what a soft impact oscillator, and over here we see that M is undergoing oscillation. It comes in contact with this surface, and then once there is contact, there is an external restoring force that acts on the object. So so what happens is that the dynamics changes after the point of impact. This is the steady state period to orbit. And once again, the idea is to look at what happens to the trajectories, the perturbed trajectories in the local neighborhood of these 2 points. So once again, we're trying to derive the discontinuity mapping. Over here, this is the actual path, and this is the perturbed path. So the path A is governed by the vector field f of I, and it undergoes an impact xi, and at this point, the perturbed vector has reached the state x0. So first, we're trying to find out the time difference for x0 to reach x1. Then we're trying to estimate the point x1 on the surface. And once we get x1, the idea is to Taylor expand xi back in time, delta, but now x1 is governed by the vector field fj. So the idea is that once the perturbed vector reaches the point x0, we simply map from x0 to x2, or from y minus to y plus, and that is the discontinuity mapping. So once again, we end up with a quadratic equation in delta, and this is basically the higher order transverse discontinuity mapping. If you see, so this was again, we get the same expression as Professor Mpuleni showed. Now that's the thing is that you can see that this is always real. And also there are no additional parameters that the system depend on. For example, damping, the impact time, and other parameters, they don't appear over here. But in the second order correction, we start considering these parameters, and therefore this makes the flight time estimate more accurate. And now, once again, if you look at the transverse discontinuity mapping, if you substitute delta over here, you substitute the first order delta in these expressions, you can simply factor out y minus. So you get an identity matrix plus fj minus fi divided by the gradient of f dot fj. So that is the solvation matrix. But now with higher order correction terms, we cannot express a state transition between y minus and y plus. So this is an instance where an impact is occurring. And at this instant, we are trying to see what the function g looks like. So this quadratic equation is simply written it as g. And then so g now depends on delta as well as the components of the perturbed vector. So the higher order theory tells us that impacts only occur when these two surfaces sort of meet at this plate, or it actually, when these two planes meet at a certain point, and the locus of these two curves for which impacts occur is given by the two roots of the function g, and only the one with the positive sign makes sense. Now, similarly, if you plot the imaginary part of the root over here, we see that, so this is the imaginary part of the delta and the real part of the delta, and we are changing the perturbation. The first component of the perturbation, y1, we see that the imaginary part of delta is only 0 for a certain range of y1. So that means impacts will only occur when perturbations are limited between these regions. So this is an example where we're seeing that an impact does not occur. The black trajectory is the true solution of the perturbed part. The primary orbit is undergoing an impact. But the first order tells us that impact will occur after a finite amount of time. But the second order gives us an imaginary value telling us that impacts won't occur. Similarly, in the bottom two pictures shows us what happens when actually impacts occur. So this is the application of the first order transverse discontinuity mapping, basically the solvation matrix. The perturbed path comes over here, x0 gets mapped to x2, and then we continue integrating forward. But you can see that there is a slight shift in the phase when we compare it with the exact solution. But if you consider the higher order mapping, we see that it actually coincides with the path. So this is much more accurate. Now, the main thing is that we require a state transition matrix, basically a solvation matrix that comprises these higher order correction terms. So what we do is we consider a small, like for an n-dimensional non-smooth system, we consider n perturbed vectors that are initially lying on a hypersphere with a very small radius, and we let the primary limit cycle evolve along with all these n hyperspheres. And what happens is it undergoes an impact, and now we have n vectors, n perturbed vectors y minus, which is ready to get mapped from y minus to y plus. We simply construct a matrix where each of the column entries becomes the vectors y minus for all n vectors, and simply there are two matrices, and we can simply invert them to get a solvation matrix. Now, to verify whether we have got the correct solvation matrix with the higher order correction terms, is simply we proceed to calculate the Monroe matrix followed by an eigenvalue analysis to get Floquet multipliers. So when we do that for the impact oscillator, we see that the Floquet multipliers indeed correspond well with the bifurcation diagram. We see that one of the Floquet multipliers reaches -1, and then there is an instantaneous bifurcation from a period 1 to period 2. This is for the impact oscillator, and similarly for the soft impact oscillator, we see that when we are trying to decrease the parameter, the Floquet multipliers are evolving, and then eventually it becomes 1. Telling us that the existing period 1 orbit will become unstable, and immediately we see a period 2 orbit at that instant. So the Floquet multipliers are indeed correct. Next is that Floquet multipliers are only valid for periodic systems. So we need to verify whether it works for aperiodic systems as well, because there are chaotic bands as well when you're observing periodic cascades in impact oscillators. So we do that. We just let the system integrate the perturbed vectors are integrated using obeying the Jacobian of the vector field. Well, the only difference is that during an impact, the perturbed vectors get mapped from y minus to y plus using the higher order. scheme. So once again, we see that when we compare it with the bifurcation diagram, we see that we do get positive diagonal exponents corresponding to chaotic trajectories for the impact oscillator, and for the soft impact oscillator, we see that one of the Tokyo multipliers based on the largest the largest diagonal of exponents, they become 0, and at that point period disappears into period 2 order. So that concludes my work. So the idea is that second order flight time is necessary when deriving the discontinuity mapping. So in papers, it's usually written that even if you take higher order corrections, you don't get that much better results, which is true. The thing is that instead of looking at the Taylor expansion of the states, if we look at the Taylor expansion of flight time, and if we end up with a quadratic equation, which is much more accurate. So if we use the quadratic flight time, that gives us a better result, and it also tells us whether impacts will occur or not. And it also defines the order in which solvation matrices should be multiplied to get the correct monotomy matrix. So we've derived the second order flight time. We've also derived the transverse discontinuity mapping for both hybrid and Filipov systems. From there, we have considered a method where we can invert and get a higher order solvation matrix. And some of the limitations of this work is that when perturbations become very small, like in the order of 10 to the power minus 4, both the results are very similar. That's one drawback. The second thing that I'm currently working on is looking at the higher order transverse discontinuity mapping for Filipov systems, but now considering sliding case. I've not looked into sliding yet. And the third pending work, which I want to do, is considering higher order corrections of the Nordmark map, so that we can correctly predict when bifurcations, like when large amplitude chaos occurs in impact oscillators. Thank you.